Good morning. My name is Bob Rakowski. I'm here with the healthcare group at JPMorgan. It's my pleasure to introduce our next speaker, Jason Kelly, co-founder and CEO at Ginkgo BioWorks. Jason, I'll pass it over to you.
Thanks, Bob. Thanks for having me. Hi, I'm Jason Kelly. I have to say I like being around people. So I'm pretty bummed we all get together this year. I did put my email address up on there. I think one sort of good thing about Zoom world is it's easy to quickly grab a virtual meeting. So if you like anything you hear today and you want to talk more, please don't hesitate to reach out to me directly. I am craving human contact. All right. Okay. So to jump in, I want to give a little bit of background on Ginkgo, and then I'm going to scope out a little and explain sort of the field we're in, synthetic biology, because I'm getting more and more people asking about this on the investor side. And then I want to spend about half the talk talking about where I think this technology runs up against what's been happening in the COVID-19 response. So a little bit of background on Ginkgo. We're about 500 people, based largely in Boston, although we have a lab out in California as well. Big investment in robotic automation, which I'll talk about briefly in the technology. We've raised about $930 million. Private investment over the last 5-6 years. Largest investor is Viking Global. Most recent round was done by T. Rowe about a year and a half ago, valuing the company at $4.5 billion. Notably, about a month ago, we announced a $1.1 billion that we were approved for a $1.1 billion loan from the U.S. government through through DFC, which I'll talk about as part of building out our COVID-19 sort of biosecurity response. And so again, I will touch on that today. And then I've got these big numbers in the corner, which I'm trying to use to remind myself to tell you what slide we're on. So we're on slide 2, since you guys are going to be, you all will be advancing yourselves. Okay, so third slide. So what is synthetic biology? So the fourth slide, you can see the Economist cover from April 2019, says redesigning life, the promise of synthetic biology. That same year in November, the White House held a synthetic biology bioeconomy summit. This was a follow-up from similar summits in AI and quantum computing. And the general idea is this is a category, an emerging technology category of national importance. That was sort of the idea behind these summits. And so I want to explain, how to get it in your head, particularly folks that have a lot of experience in the biotech pharma sector. How do you think about this emerging area, synthetic biology? How does it play with sort of genetic engineering in that space? So I'll give you my favorite sort of nerdy description of what synthetic biology is. And so to help you understand that, I really like this photo on the left up here. This is one of the co-founders of mine here at Ginkgo, Tom Knight. And Tom was on the faculty at MIT starting in the early 1970s. So that picture is from 1972. That machine in the middle, that was Tom's master's thesis. That was a mini computer at the time, just so you get a sense of the era. So Tom went from programming kind of mainframes to mini computers, personal computers, early internet, taught the semiconductor design course for many years. And in the mid-1990s, he decided the interesting thing to program in the future, not going to be computers, it's going to be cells. And his core idea, and I think this is really the core idea of synthetic biology, is that you can program a cell like you program a computer because it runs on digital code in the form of DNA, right? It's A, T, C, and Gs, not zeros and ones, but you can read that code with DNA sequencing and genomics, and you can write that code with DNA synthesis, DNA printing. And if you can read and write code and you have a machine to run it, that's programming, right? And so Tom's idea was, heck, I've been building programming tools for 20 years. Maybe I can help. And so to his credit, in his 40s, he starts taking undergraduate biology lab classes. He sets up a wet lab in the computer science building at MIT, and he shifts his focus from computer architecture to molecular biology, biochemistry. And he looked at it differently. He asked the question, well, what are the programming tools like to program a cell? And his conclusion was, oh, they're horrible. Right? They're like laughably bad. You use your 2 hands at a lab bench, PhD trained person to flip 1 A to a T or 1 C to a G in the genome in an afternoon of work, right? And so Tom was like, well, that's like a 0 to 1 on a computer. If that's the rate that we were programming things, why would you even try to write any apps, right? And so Tom's view, and he kind of indoctrinated the rest of us that founded the company with him when we met him in 2002, with this idea that what we really need to work on is the platform and tools that make it cheaper and easier and faster to program cells year over year. And then all the applications will come. And so that I think is a core concept in synthetic biology. It's like an infrastructure area. Its focus is not on, even though there's going to be applications, apps in pharma and agriculture and food, those are the applications. What SynBio really is driven by is the underlying tool and platform technology infrastructure that makes those applications possible. Okay, and so what does that look like today? This is on slide 6. Is a picture of our newest facility getting qualified here in Boston. Again, we have about 200,000 square feet of space. This metal tracks in the middle are these like magnetic tracks that basically move little almost like train cars around that can control hold labware. Those robotic arms can pick the plates up and down off the tracks, and you can connect that to various automation equipment. And the idea is to apply manufacturing theory and automation to the kind of work I did back when I did my PhD at MIT, of that scientist doing that genetic engineering protocols at the bench. And the key idea behind this is when you run it like a factory, you start to get scale economics like a factory. So we've seen over the last 6 years, roughly a tripling in the output of our facilities here in Boston and a halving of the cost per operation in that facility. So this is a scale economic. It's like semiconductors or automobiles. And we call it Knight's Law after Tom, kind of like Moore's Law. And you can see some of our output numbers there. Similarly, you see similar scale economics in DNA reading and writing. So what I just showed you there was really lab automation and software being applied to molecular biology techniques. Here you're seeing the cost curves many of you are likely familiar with in darker blue there in genomics. The cost to sequence a human genome going from $100 million in 2000 down, depending on what you believe today, to about $100. And then also the cost of writing DNA. So, printing a piece of DNA on a per base pair basis now down in the pennies per base pair. And Ginkgo's the largest user of that second technology, DNA writing. So we think about 20-25% of worldwide DNA printing. We're Twist's largest customer. We acquired, Twist is about an $8 billion market cap public company in the DNA writing space. They're kind of like the Illumina of DNA writing. We acquired one of their competitors about 4 or 5 years back called Gen9. So we have some of that in-house in the lab behind me here. And then I'll talk about this a little later, but we announced a $150 million partnership with Berkeley Lights, which is another key technology in the area of sort of debugging cells, like analyzing what's going on inside. And I'll touch on that as part of our work that we've been doing in COVID. So if you go to slide 10, so how does Ginkgo fit into this sort of industry ecosystem? What do we sell? What's our platform? And you should really think of us as a horizontal platform for programming cells independent of market. And so I'll talk about some of the different apps in a minute, but I'll note, we have done things like we launched about a little over a year ago now a fund called Ferment Fund, which is a $350 million investment vehicle to back new spin-out companies on top of the platform, new apps. Okay, we have a partnership with Y Combinator to make it easier for new startup companies to launch without having to make big laboratory investments. And so in biotech, there's not too many great horizontal platforms, in my opinion. But in tech, the obvious analog would be something like Amazon Web Services, right? Amazon has these big data centers. Some of them are used to stream movies. Some of them are used for electronic medical records. It doesn't really matter. It all uses the same core infrastructure, and that core infrastructure has a big economy of scale. And importantly, Amazon makes the big fixed cost investment so that you as the customer get the low marginal cost of compute. That's exactly what we're doing here. We've made a very big fixed cost investment in the facility that I'm in to put in all the automation and infrastructure to give you, our customers, a low marginal cost of doing cell programming and genetic engineering. And we want to get as many people using that as we can. And so that's sort of how we think about our business. And we make money through people either paying us for that service work. And then importantly, as the apps go out the door, kind of like Apple App Store, we take a royalty on the sales of products that are coming out of apps developed on our platform or equity in the company. So to give you an example of some apps, this is one of my favorite ones because people don't think of this as biotech often. So this is Impossible Burger. So if you ever had the Impossible Whopper at Burger King, you bite into this thing and it bleeds. It's a veggie burger that bleeds. So where does the blood come from? On slide 11. And so where it comes from is Impossible has programmed a cell to have the gene for hemoglobin. They produce that blood protein. They add it back to a veggie burger. It smells right. It tastes right. They get to call it the Whopper, right? And so we have a spin-out company called Motif that's now raised over $100 million, doing similar things with egg proteins, milk proteins, things like that, to get these animal proteins that would be available to the next Impossible foods. Similarly, we have a $100 million joint venture with Bayer Crop Science to engineer microbes to produce fertilizer for crops. We have over $100 million deal with a large Canadian cannabis company that Altria is the largest shareholder in to try to produce small molecule natural product cannabinoids without having to grow the plant. Instead, we've engineered that into a yeast or bacterial cell. And in fact, in the last year, they've now built out pilot manufacturing facilities and are producing first products here. And then we have a partnership with Roche. We acquired a company called Warp Drive Bio, a Third Rock Ventures-backed company a few years back. That focuses in the area of natural products for antibiotics, right? And so you'll notice sort of in this case, the natural product work we would have done in cannabinoids doesn't look all that different than sort of the natural product work here in antibiotics. And so a lot of the infrastructure in that case is very, very similar between those two projects as one example of the reusability of the platform. We also announced just in, I guess it was in October of this year, new spin-out companies backed out of Ferment Fund with $40 million of investment called Alonia, pursuing wastewater cleanup. You might be familiar with chemicals like PFAS that end up as being difficult to degrade environmental pollutants. The focus of Alonia is to go after that half of biology that breaks things down and commercialize those products. Okay, and so that's a very wide swath of different apps. You know, 5 or 6. We have about 50 app development projects ongoing on the platform today. So this is just a handful of them to give you a sense of the range of things that you can program biology to do. So I'm not going to belabor that a lot more today. I wanted to just point out again the takeaways. Horizontal infrastructure, kind of like an Amazon Web Services, improves with scale. Our attitude is to get as many folks developing apps as possible on top of it. We want to give a lot of the value back to the app developer and take a small piece, kind of like the App Store. That's the general model for Ginkgo across a range of industries. All right, so I want to spend the rest of the time here in the talks talking about COVID-19. So I showed on slide 16 that April 2019 Economist cover. And I was very excited, look at all the things that biology is going to do for the world. And then here's the March 2020 Economist cover, which shows what happens when what biology can do to the world negatively. And so I think one thing we need to keep in mind as we build out these technologies is that because we haven't been hit by sort of a true pandemic class agent like this since 1918, we are lacking the global scale biosecurity infrastructure that really we ought to have. And I generously, who knows? It had been 100 years, right? Like maybe modern healthcare and this, that, and the other thing would have made it so that this couldn't have been this bad. But the reality is, it has put the whole world on its butt for a year now, and I think likely to be another year following. And that's sort of a level of exposure that is kind of intolerable. And so we do need to now build out global scale biosecurity infrastructure so that can't happen again. So I want to talk a little bit about what synthetic biology can do. Platform companies, just in practice, since we just lived this the last 9 months in the instance of a response to a pandemic. So back in March, Ginkgo opened up our platform initially for free, $25 million of free platform work for people working on therapeutics and vaccines. This is the set of work I'm talking about is really what led to ultimately this $1.1 billion loan from Development Finance Corp to expand this infrastructure, but I want to go through all the pieces of what we've been building. So most notably, we did a partnership with Moderna in April to work on optimizing one of the steps in their vaccine manufacturing process that went well. That's on slide 19, and now on slide 20, I want to talk a little bit about, in a little more detail, about how you make nucleic acid vaccines, because we're now supporting multiple nucleic acid vaccine developers, and I want to highlight the various challenges in this supply chain. So the first step in making a nucleic acid vaccine is to produce DNA. Okay, and the way you do that is you have a plasmid, a small piece of DNA inside a bacterial cell. You grow it up in a big fermenter, and you produce a lot of that plasmid DNA. Then you isolate the DNA from the fermentation, throw the cells away, and then you go to the lab, and you're going to take various enzymes and nucleotides and some buffers, and you're going to use those to convert the DNA to RNA. Okay, and that's going to actually amplify it. You're going to get more copies of RNA than you had input copies of DNA, thankfully, through that process. And then you take that RNA, and you put it in a lipid nanoparticle, and depending on the company, there's different proprietary blends here, and then that goes off into the drug product, okay, and into your arm, thankfully. Okay, so a couple steps here where synthetic biology can play a role. First, in the plasmid fermentation step. So, these are this is the first time we're producing nucleic acid vaccines at global scale. First time we're really producing them at commercial scale. And so as an industry, and so those steps to overproduce that plasmid can be optimized. And so this is important for the mRNA vaccine companies like Moderna, BioNTech, CureVac. It's more important for the DNA vaccine companies, so a company like Inovio and others that are basically producing DNA that will then go directly into that drug into that drug product. They need even more DNA produced because they don't have that RNA amplification step. Okay, and so there's two issues here. One is to optimize that DNA fermentation, and Ginkgo's done a lot of great work there, and like I said, working with a couple companies there. And then the second category is in the inputs into converting DNA to RNA. And the challenge here is that these have historically been lab reagents, right? Like, why have you needed to turn DNA into RNA? Because you're doing an R&D experiment, frankly. And so now suddenly we need a ton of this stuff in order to produce really global quantities of the vaccine. And I think this is really apparent as you start to scope beyond the 300 million people in the US and start to think about the 8 billion people on the planet. If you wanted to get RNA vaccines, which are proving to be quite efficacious, out to a wider swath, you're going to need huge amounts of these inputs, and they need work. So that's the second area. Over the last 6-7 months, we've been really working to create new methods to produce those at high quantities that we're getting out in the market soon. So those are sort of the two areas we've been operating when it comes to nucleic acid vaccine production. The other area we've been investing in is in sort of therapeutic antibodies. We have a nice partnership here with Toshient. I think it's a good demonstration of kind of some of the new edge things you can do with the platform. So the idea here is to go looking in convalescent patient samples of either lung fluid or blood to go looking for candidate neutralizing antibodies. Okay, and we find those with our partner Toshient. We find the sequences, then we synthesize those, use our relationship with Twist, and then clone those in a high throughput way using our automated infrastructure into mammalian cells to produce those antibodies. And then those antibodies go into high throughput screens, in this case, in a microtiter plate, to look for both binding and neutralization. And the reason we look for binding is because these antibodies can also be useful for diagnostics and neutralization for therapeutics. Okay, and so we've been moving this technology over to the Berkeley Light System, which is basically small nano pen chambers, which are kind of like little teeny wells on a microarray chip. And the way the Berkeley Light System works, you can put individual cells into those wells with optical tweezers, and then you can look at a single cell, like you can see in the middle of slide 24, that little green dot there. You can look at an individual cell and see if it got infected or not. So in this case, this is a cell that basically turns green if it gets infected. And so the way our process works, and you can see some of the data on the right, is we will put a test cell like that, plus a cell that expresses a novel antibody in the well together. We'll flow a virus through, and if the cell gets protected by the antibody, it won't turn green. If it doesn't, it will turn green. And you can see the red line is one turning green, the blue line is one not turning green. We think this will let us really screen vast amounts more antibodies through these types of techniques, and so we're really excited about this. So this is an area you or companies you're involved in are interested in. We think this has broad applications in antibody work in general. Okay, the other areas we've done some work. We did a lot of DNA synthesis. Here's a set of plasmids we built and donated into Adgene and BioBricks Foundation to go to researchers working on COVID-19. On slide 26, we've been investing a lot in increasing our DNA sequencing capacity. So to date, we've sequenced about 4,000 whole genome sequences of positive SARS-CoV-2 samples. You might have read about the new UK variant B.1.1.7, as well as in South Africa, there's a concerning variant. We should expect that as vaccines go out, there will be selective pressure on the virus to mutate and evolve around our vaccines, and also to involve potentially increased infectiousness. That's already the case with B.1.1.7, it really looks like. And so right now, the U.S. does not have, there's been about 50,000 deposited sequences into the big database from the U.S. We don't have a regular kind of the equivalent of what we have for the weather, right? Monitoring satellites that report out on the status of the day. We absolutely do not have that when it comes to the genomic status of this virus. We absolutely do need to build that. So there's a nice New York Times article here about this, but this is one of the big things that, frankly, I think we have an obvious opportunity to build in the context of these new variants. And if we build it, then we have it for the future, which I think is a really important thing for the country to be thinking about. So on slide 27, the other thing in this category of things I think we should build for COVID that we will then have for future pandemic defense is testing, but not diagnostic testing. Okay, so Ginkgo is not involved in diagnostic testing. There's a big diagnostic testing industry I don't want anything to do with. What Ginkgo has been focusing on is testing of people without symptoms in order to break transmission chains. So testing as a biosecurity tool, not a diagnostic tool, okay? And that is a very different set of challenges. For number one, you're not gonna get tested in a doctor's office or a drive-up testing center because you don't have symptoms, right? And the CDC just released a report a couple weeks back saying about 50% of the cases now they estimate to be transmitted by people with no symptoms, right? How the heck do you test these people, right? Like, how does a person decide to go get a test? It needs to be ridiculously convenient and ridiculously cheap if we're going to use this as a tool. And there has been success in this sort of broad kind of monitoring and surveillance style testing in things like keeping universities open in the fall that did regular testing of their students. So we know this works. It's just the numbers are huge if you imagine using it as a population scale. So on slide 28, thing I'm most excited about coming up in this area is using testing in the context of reopening K-12 schools. So about 50% of the schools in the country today are closed. This is enormous negative social impact, as in particular sort of underrepresented groups, people with lower socioeconomic status are disproportionately impacted because they cannot create really effective at-home schooling environments. And I have a 6-year-old and an 8-year-old. At-home schooling just is difficult all around, all right? For those of you who are parents, you know this. So getting schools open through regular testing of students, I think, is one of the best ways to efficiently go out and start to build this sort of monitoring capability where we are able to identify an asymptomatic case before it spreads and break that transmission chain. And so I'm excited. Massachusetts just announced that they're doing a test of this in slide 29. We at Ginkgo have launched through Concentric, our brand in this area, a nationwide K through 12 testing pilot for free. The way this works is we do a classroom test. So 20 students all get swabbed. The swabs all go in a tube together. They self-collect. The tube gets sent off to the lab tests it, and the classroom is a yes or the classroom is a no. So totally different than diagnostics. You're not testing people individually. You don't even know which swab goes with which person, right? This is a monitoring technology, and it's testing in services of biosecurity. And so you can see, actually, I've really good experience doing this in classrooms already. Really excited about this, but I think it's one of the big tools that the U.S. needs to invest in coming up, and it looks like Biden and his team have made that a priority. And then finally on slide 30, I want to tie this back to synthetic biology, these activities in biosecurity. So look, Ginkgo's stated goal is to make it as easy to program cells as it is to program computers, right? I want millions of people programming cells. I usually end these talks, if you've heard my talks at JPMorgan before, talking about all the amazing things that biology can do, and like, look at a plant, the thing grows itself and repairs itself, it makes free solar panels, the whole thing. Isn't biology incredible, right? This year, isn't biology powerful, right? I mean, just the economic and social damage of 28,000 letters of DNA right now is a bit staggering. And so if we're going to build the tools that make biology easier to program, we have a responsibility alongside that to build the biosecurity tools that allow us to do that safely and responsibly. And it's essential because, man, we want to deploy biology all over the economy. It's going to make, it's going to provide food security. It's going to help climate change. It's on and on and on. But we got to do it in a way that's safe and responsible. I think we're not done with COVID. I like this pin. I found this. This is from the Volunteer Medical Service Corps in 1918. This was sort of a group that got stood up to surge doctors and nurses around the country in hotspots. And this article is 3 days old, right? Like we just had the most deaths in the country since the beginning of the pandemic. We were right in the middle of the worst part of this whole thing nationwide. I know it's been a lot, and so it doesn't feel that way. It feels like we should be done with it, but we're not. And so I think our industry in general and synthetic biology in particular still has things we can do to throw more tools at this prior to the vaccines, which I'm so proud to have come out of the biotech industry to ultimately put this thing to bed. But we have a lot of work to do in the next 6 months. So if you go to slide 31, that's my email address. If any of this is interesting to you, I'm more than happy to chat about it on the investor side or the partnering side. And thanks so much for your time.